Morning again. Math 323, or if you're in the master's program, Math 755, which is the first course in ordinary differential equations. The textbook is free. It's available online, and I posted the entire book on Blackboard. So you do not need to buy a textbook for this course. It's actually a very good book. The author basically opened it up to the world to use at no cost. So that's very nice. We're also going to use a little bit of computer algebra program called Maple, which you also can get for free from CUNY. And we don't need it yet, but I will send out information about how to download the software from what is called the CUNY email. And there'll be some information about how to use it. It's a way to solve a differential equation, it's a way for your computer to solve a differential equation, which is pretty good. We are going to cover the first few chapters of the textbook, certainly chapters 1 and 2, which will take us a few weeks. We'll cover completely. Chapter 1 is just a very simple introduction to the subject and introduces some definitions, which I will review. And the real material in the course starts in chapter 2. So I already posted 2 lectures on YouTube with the first 2 lectures. Lecture 1 covers chapter 1. Again, it's purely descriptive. And chapter 2 is where we begin to do some serious work. There's homework every week. You write out the solutions, scan it, upload it to the assignment section of Blackboard. My expectation is that these Monday, Wednesday lectures will be on Zoom. There may be some in-person problem sessions on campus. The one thing that will definitely be on campus are the midterm and the final exams, so that you have to keep in mind. And I think the dates of those are already posted on the Blackboard for you. Questions? What can I answer about the course? Any questions? No? Okay, so let me just show you the textbook again for a moment. This is it. Elementary Differential Equations with Boundary Value Problems by William Trench. And if we turn to the table of contents, the introduction, chapter 1, is the subject of the first lecture, and there's some homework problems for Tuesday of next week. Monday is Labor Day, so there's no class. And then we start chapter 2 on first order equations. And the most important section is section 1 on linear first order equations, and we'll learn how to solve them. Linear equations come up very often in applications, and we will look at numerous examples of them. And then we study what are called second order equations. And basically, we don't go any higher than second order equations. There's not much reason for us to do that. So let me turn very quickly to chapter 1. I'm just, again, this is what I covered in the first lecture, which is already uploaded to Blackboard. But these are the topics, and I'll just review them a little bit right now. Let's see, there's something in the chat. Right, so the syllabus for the entire course is not yet on Blackboard, but there certainly will always be enough so you know what will be going on for several weeks ahead. Okay. Okay, just one second. Okay, so let me turn to a screen that I can write on. And here it is. So you should see a white piece of paper that says ordinary differential equations. And I just want to very quickly review and maybe do one or two homework problems from chapter 1. So the first question you might ask is, what is a differential equation? And what makes a differential equation ordinary? So a differential equation first of all, it's an equation where you have to solve for something. I mean, what's the usual kind of equation that you, or the first kinds of equations that you have to solve? You might have to solve something like 3x plus 7 equals 13. And you have to find x. And you say, well, 3x equals 6, x equals 2. So the answer is the number 2. So a differential equation is an equation where you have to find something. And a differential equation is an equation in which the unknown, what you have to solve for, is a function. So, for example, you might have an equation that says 2y equals x squared plus 3. Find y. And the solution would be y equals a half x squared plus 3 halves. So that would be the solution of this equation. This is just an equation where the unknown is a function, but it's not a differential equation. A differential equation is an equation in which, first of all, the unknown is a function, and the equation includes some derivatives of the function. So an equation like y double prime second derivative plus 8y prime plus 9y equals cosine x. This is an equation where the unknown is a function, and you want to find a function that solves this equation. Or let's make something easier. Say y prime equals x squared. Find a function y whose derivative is x squared. So this is a very simple differential equation. Of course, this differential equation is something you learned to solve in first year calculus. This just means find an antiderivative of x squared. So the solution is the integral of x squared, right? Because the derivative of the integral is x squared. So this is a third x cubed plus a constant. So this is a very simple example of a differential equation. The unknown is a function. This makes something that looks maybe even simpler. Y prime equals y. Now, this is a little bit more complicated because you can't just integrate something simply to find what y is. On the other hand, you proved in calculus that if you take the function y equal to any constant times e to the x, that y prime is also c times e to the x, which is y. So for any number c, this function is a solution of this differential equation. So this is a little bit harder than the first example, but it uses some calculus, but of course you know calculus. I should say in both of these two examples, there was this arbitrary number c. For any value of c, you get a solution. And this number C is called a parameter. Parameter is just another name for a number. And because there's one parameter in each of these solutions, each of these is called a one parameter family of solutions of the differential equation. And you can prove that for any value of C, you get a solution. And conversely, we'll also prove that every solution is of this form for some value of C. So typically, when you're looking for the general solution of a differential equation, it involves one or more arbitrary parameters. And for every choice of those parameters, you get a particular solution. But the general solution typically involves some parameter. If you look at these two differential equations, you'll see that in this differential equation, the highest derivative is the second derivative. In this differential equation, the highest derivative is the first derivative. And what is called the order of a differential equation is simply the highest derivative of the that occurs in the equation. So this equation, which involves the second derivative, is called second order, DE, differential equation. This equation, which involves just the first derivative, is first order. It's first order differential equation. And yeah. Oh, I should also say, what makes a differential equation ordinary? Ordinary differential equation, these are all ordinary differential equations. They involve a function of just one variable. So a differential equation is ordinary if it involves only one variable. And the variable is usually either x or t. I mean, you can choose any, just like in calculus, you can use any variable, x, y, z, a, b, c, r, s, t that you like, but typically we use x or t. Sometimes our differential equation is modeling something that is evolving in time. So we often think of a differential equation that in which the variable is t. The t stands for time and something is changing in time. But that's just an interpretation. Again, it never matters what letter you use for your variable. A partial differential equation, that's the other type of differential equation. Partial differential equation involves two or more variables. And then the derivatives are partial derivatives. So for example, if we take the second partial of y with respect to x squared, and the second partial of, actually I should call this, let's call my function f. So f is the function z, is some function f of x, y, a function of two variables. If you take the second partial of f with respect to x and the second partial of f with respect to y, say you want to solve this equation. Find all functions of two variables. So if you take the second partial with respect to x and the second partial with respect to y, you get 0. That's an example of a partial differential equation. This is an example which comes up infinitely often in physics, for example. And many of the equations that come up in physics are partial differential equations. But you can study partial differential equations and ordinary differential equations, and that's what we're doing in this course. So a partial differential equation involves two or more variables. An ordinary differential equation involves just one variable, and that's all we're going to, that's what we study in this class. And I always write ODE for ordinary differential equation. Okay. So this is just the introductory nomenclature. And there's several examples in chapter 1. Okay. So in general, an nth order differential equation has the nth includes the nth derivative of unknown function y and no higher derivative. And in many cases, you can take the nth derivative and isolate it somehow, solve the equation for the nth derivative. So your nth derivative is some function of the variable x, the function y, the first derivative, second derivative, up to the n minus first derivative. This is in some sense the general nth order differential equation. So if you had something like x y double prime minus cosine x times y prime plus 3y squared equals the arctangent of x, that's a differential equation. And you say, well, it's not exactly of this form, but you can always put it in this form if you wanted to. This would be x y double prime. Just bring everything else over on the left. Cosine x y prime minus 3y squared plus arctangent of x. And then you want to divide by x. And now what you have over here is some function of x, y of x, and y prime of x. So there's almost no need ever to do this, but this is just to point out that differential equations don't have to be expressed in exactly this form when you start, but typically they can always be arranged in that form if you wanted to. And this is an example. Now, we usually look for what are called solutions of a differential equation on an open interval. And the open interval, AB, this is the set of all x, real numbers x, such that x is strictly greater than A and strictly less than B. It never includes the endpoints of the interval. That's what open means. So an open interval is just an interval that looks like this. And a solution of an ordinary differential equation is a function y that solves the equation for all x in some open interval. Okay. It doesn't make any sense to talk about a solution of a differential equation at an individual point. We want a solution to be a solution that works for all x in some open interval. So let's give an example. Here's a differential equation. Xy prime plus y equals x squared. So this is an ordinary differential equation. It involves a function of just one variable x. It's first order. And because the highest derivative is the first derivative. And you can verify, you can check that if you take the function y equals x squared over 3 plus 1 over x, this is a solution on the open interval. You can go from open interval from 0 to infinity, and also on the open interval from minus infinity to 0, right? Notice, since you're dividing by x, this function is not defined when x equals 0. Right? Why is this a solution? You might say, how did I get this? Well, you'll learn very soon, that is within a week, how to solve this equation yourself. But if you're given a solution and told that it's a solution, you don't have to believe the person who's telling you that. You shouldn't, in fact. You need to check. So if I take this function and I differentiate it, y prime is equal to, see, derivative of x squared is 2x over 3, and the derivative of 1 over x is minus 1 over x squared. So y prime is equal to this. So xy prime is equal to 2/3 x squared minus 1 over x. And xy prime plus y, this is xy prime, 2/3 x squared minus 1 over x, plus y, that's 2/3 x minus 1 over x squared. Let's see, what do we get? So we have the differential equation xy prime plus y equal x squared. And I claim that x squared over 3 plus 1 over x is a solution. So xy prime is 2/3 x squared minus 1 over x plus y. Oh, y, sorry. I should always write things down correctly. Makes sense. Y is x squared over 3 plus 1 over x. 2/3 x squared plus x squared over 3 is x squared, and minus 1 over x plus 1 over x is 0. So xy prime plus y does equal x squared. So this checks. So here we have a differential equation. This is a solution because if you plug this function into the equation, it works. Okay. Are there any questions about this? Yes, 1 second. Just trying to make a note of who's here today. Okay. Good. By the way, if you had this equation, it's interesting to look at for another second or two. This differential equation was xy prime plus y equals x squared, which we could have written as xy prime equals minus x squared minus y, or y prime equals x minus y over x. So this is a function of x and y. This is just putting this first order equation into that kind of standard form I had mentioned earlier. Let's say a little bit more about differential equations. Again, for this differential equation, the solution is y equals one solution, x squared over 3 plus 1 over x. That's a particular solution. Let me look at another example. This one's much easier. This is just calculus. Suppose we have the first order differential equation, y prime equals x cubed. So the solution is y equals the integral of x cubed, which is a fourth x cubed, 1/4 x to the fourth, plus any constant. So this is what we can call the general solution. For any value c, you have a solution, and every solution is of this form for some number c. But often we start with some initial condition. So we want to find the solution of the differential equation which solves the initial condition. For example, suppose the initial condition is that y equals 3 when x equals 0. So in that case, we have y. So here's our solution. Y of x is 1/4 x to the fourth plus c. If you let x equal 0, y of 0 is supposed to equal 3. So that's 1/4 0 to the fourth plus c. This is just 0. This is c. So c equals 3. So the particular solution of the differential equation which satisfies this initial condition is y equals 1/4 x to the fourth plus 3. That's the only solution of the differential equation which satisfies the initial condition. So very often, so the typical problem in ordinary differential equations is to find the general solution to a differential equation, and then find the particular solution that satisfies some condition. Okay. Any questions about any of this? All right, let me do one or two of the homework problems just to start. So the homework is in two parts. The first is in section 1.2. First problem says, find the order of some differential equation. So for example, this is part of problem 1. If you have the equation y prime minus y to the 7th equals 0, the highest order derivative is first. So this is first order. if you have the equation y double prime times y minus y prime squared equals 2, this is a first derivative. This is just a function, which is the same as the 0th derivative. This is a second derivative. That's the highest derivative. So this equation is second order. Okay. Suppose we look at problem 3a. Actually, I'll make it more interesting. Problem 4a. We want to solve the initial value problem. Y prime equals minus x e to the x, with the initial condition that y at 0 is equal to 1. So the first thing we have to do is find the general solution. But this is easy, or at least it's calculus, because this is just, there's no y on the right side of this equation. Just find a function whose derivative is minus x e to the x. So y is the integral of minus x e to the x dx. Or minus the integral of x e to the x dx. And how do we do this integral? I guess we can integrate by parts. If I write this is x and e to the x, then this is 1 and this is e to the x. So this is minus, so the integral of x e to the x dx is x e to the x minus the integral of e to the x dx, which is minus x e to the x minus e to the x plus any constant. So it looks like the solution is x e to the x minus x e to the x plus e to the x plus a constant. Or I can write this slightly more concisely as e to the x times 1 minus x plus c. So everybody makes mistakes. I make lots of mistakes. So let me just check to see whether this really is a solution of this differential equation. If y is equal to e to the x times 1 minus x plus c, y prime is equal to e to the x times 1 minus x, derivative of the first times the second, plus the first times the derivative of the second times minus 1. So this is e to the x minus x e to the x minus e to the x. These cancel. This is minus x e to the x. Oh, so this is correct for any value of c. So y is equal to e to the x 1 minus x plus c. And at x equal to 0, y of 0 is equal to 1. And when I plug x equals 0 into this, I get e to the 0 times 1 minus 0 plus c. E to the 0 is 1. So this is 1 plus c. So this says that c equals 0. So my solution is y equals e to the x 1 minus x. That's the particular solution to the initial value problem. Any questions about this? And there are several, I mean, there are a number of problems. Most of them are fairly quick, which is partly a review of calculus, which is very important, and partly just to get used to this notion of what is a differential equation, what is a solution, And in some cases, how do you actually find a solution? Okay. There's one other section, section 1.3 in chapter 1, which gives a kind of a geometrical understanding of what is a differential equation. Because if you have your differential equation, let's say it's first order, and you can write it in the form, so this is a first order ordinary differential equation. And we write it as y prime is some function of x and y. And suppose you have a solution of this equation. So the solution, let's say you graph it, it's some curve in the plane. That's the solution. And if you take any point xy, well, this is actually, why is point xy, but take any point xy, this is the curve f of xy. So what this says is that at any point xy, the derivative y prime is f of xy. What is the geometrical interpretation of the derivative of a function at a point? It's the slope of the tangent line. So this says that at any point xy in the plane, if a solution goes through that point, then for that solution y, the slope of the tangent line is given by f of xy. So at this point on the curve, the tangent line has slope f of xy. So it's as if you take the point xy and you draw a line through that point with slope f of xy. You have a kind of, you might call this a direction arrow. And if you had a curve, you had a solution to this differential equation that passes through the point xy, the tangent to the curve at this point will be in this direction. So the curve will look something like that. And if you're given the differential equation in this form, at every point xy in the plane, you could draw a little arrow whose slope was f of xy. And you get what is called a direction field. It's extremely hard because it's just too much work to draw these things by hand. A computer algebra program like Maple will draw a direction field for you. But if you're given a direction field, and there's several examples in section 1.3, that gives you some sense of what the geometry of a solution to your differential equation looks like. So here's an example from the text. So here's the differential equation. You can just turn to your book on page 18. Y prime equals x minus y over 1 plus x squared. And here you have a rectangle, part of the plane. And you see at every point there's a little arrow. And that means that any solution to this differential equation, if you draw the curve, at every point the tangent will be in the direction of the arrow. So if you look at these arrows, that gives you a whole family, because in general, a differential equation has a first order, has a one parameter family of solutions, has infinitely many solutions, but they're all given by curves, and these curves are always in the direction at every point of the direction field. So this is a nice example just to give you some understanding geometrically about what a differential equation of the first order tells you. It tells you the direction of a curve at every point. And the solution is somehow a curve that interpolates between all these direction arrows. There's these direction arrows everywhere. And there are one or two problems to that involve direction arrows. Typically, the problems give you the direction field, and they just ask you to sketch in some solution curves. And it's a useful exercise just to understand the connection between the geometry or the shape of a curve and what the differential equation is telling you. Okay. Let me just make one last remark, and then we'll be done for this morning. So chapter 2 is on first order equations. So the only derivative in the equation is a first derivative. And these can be very complicated. You could have something like y prime cubed times y plus the cosine of y times e to the x plus y prime squared x equals 7. So this is a first order equation. They're high powers that you see in the equation, but the only derivative that occurs is a first derivative. This equation is close to impossible to solve. Just because you can write down an equation doesn't mean you can solve it, doesn't mean anyone can solve it, doesn't mean there's a solution in any reasonable way. So when you begin to study equations, you look first for the kinds of equations you can solve, and you push the boundary of that as far as possible. And we're going to start with what are called linear first order ordinary differential equations. And a linear first order equation is always of this form: y prime plus some function of x times y equals some other function of x. So you don't have y or y prime occurring to a power. You just have y prime and y to the first power, and you also don't have them multiplied by each other. There's no y prime term. It's y prime plus something times y. There's something as a function of x equals a function of x. And this is what a linear first order differential equation looks like. And any other equation which is not linear is called nonlinear. So it's one or the other. Your equation is either linear or it's nonlinear. And linear equations, we can always figure out some way to solve. Even linear equations, we divide into two cases. In the first case, this right-hand side is 0. So the equation is just y prime plus p of xy equals 0. And this kind of equation is called homogeneous. In case 2, the right-hand side is not 0. So this is some function which is non-zero, and this is called non-homogeneous. Now, if we take the homogeneous equation, one solution is just the function which is identically 0. Y of x is 0 for all x. Because if you let x equals 0, y equals 0, the derivative is 0, you just get 0 plus 0 equals 0. And this is kind of trivial. And in fact, this is called the trivial solution. And the problem is to find non-trivial solutions. Right? Okay. It's also very important to note that an equation can be linear even if at first glance it doesn't seem to be linear. So if you have an equation like x squared y prime plus 3y equals x squared, that's not of this form because I have x squared times y prime. On the other hand, there's no reason why I can't divide by x squared. Right? If I divide by x squared, I get y prime plus 3 over x squared y equals x squared over x squared, which is 1. So at least for x different from 0, I can divide by x. And this equation is the same as this equation. And now this is of this form where my p of x is 3 over x squared, and my right-hand side f of x is equal to 1. Okay. So I don't want to rush too far ahead, and I want to give you a chance to work on the homework problems from chapter 1. But on Wednesday, so I've already posted the lecture on solving first-order equations, and lecture 2. And in class, in our Zoom class on Wednesday morning, I will go over again the method for solving linear first-order equations and solve a number of problems and answer questions. Okay. Any questions about anything that I've talked about so far? Again, since I often try to post the sort of the semi-formal lectures on what's in the textbook before class, I can always then just spend the class reviewing and answering, solving problems, homework problems, or any other problems you might have questions about.
When will the lectures be uploaded to YouTube?
Sorry?
When will the lectures?
Are usually up within an hour or so of, well, they'll be up this morning. I actually have another class right after this, but they're certainly up the same day. And often within 10 or 15 minutes. It depends on, sometimes YouTube is slow, depending on how many people around the world are using YouTube, but it's always, everything gets posted very quickly. And you should have been able to find the first 2 lectures already on the playlist on my YouTube channel.
Gotcha, thank you.
Okay. Other questions? Let's see. Trying to figure out how to stop my share. Oh, I don't have to do that. That's not what I'm doing. This is what I want to do. Okay, we're done. Okay, if there are no questions, I will see you all 9 o'clock Wednesday morning. Everyone take care. Be well. Bye.
Thank you, Professor.
Thank you, Professor.
Okay, be well.